Hello guys, I apologize with the light shining on me. I'm Pat. I'm going to get more into my education and background into the X-Lights forum in a little bit. I have here with me Steve Slupski. He is a master's in electrical engineering. Steve and I actually became connected while I was trying to process the pixels. I wanted to know what I was buying. What was an 8-cent pixel and what was a 12-cent pixel? What was a 25-cent pixel? What's a $1.30 pixel? So Steve is going to help us go through. We're starting with the issues that we've known to be true with some fires, pixel fires. And first thing I think what we're going to do is I'm going to. Sorry, Steve, if you want to say hello for a second.
Hello.
There's going to be a lot more probably talking from me where we should hear a heck of a lot more from Steve. And I believe Steve has volunteered at a later time to really delve in with us. So we're skimming the surface here. We're not going to go through it. Steve has been nothing but a master in making me understand things, and if he can make me understand things, he can make anybody understand things. One second here. First, what we're going to do is we're going to take this video here and show you. I'm going to turn the volume up. This guy is his name is Jack. You probably heard of him already.
And the technical term for what he's doing here is called board separation.
Board separation.
Or depanelization.
Or depanelization. See, technical terms. What Jack's saying there is he did a really good job.
What you see in this first picture here is all the circuit boards that comprise the pixels. They're all, when you manufacture the pixels, all the circuit boards are all attached to each other. There's a score between each one of those pixels, and the purpose of this machine is to break the pixels apart, the circuit boards apart.
So, as according to, okay, so we're going to talk math. Now remember, we're going to get more into Steve's education and experience in a bit. What I want to talk to you about now, though, scientifically, accuracy, how accurate do you figure he's being right now?
With the machine.
With what he's using there. We called it the cruncher.
Yeah, I think David kind of came up with that.
Yeah, David did, yeah.
I can't remember, but we kind of chuckled about it when we first saw this video. But then as we went through this analysis process, this video came back. We all owe this guy a Starbucks card. Seriously. We should all just send this guy Starbucks cards. So we'll get hundreds of them. He deserves them because he actually helped us understand what the problem is.
What the
One
back.
of the things that we don't fully understand, and what makes it difficult to diagnose these problems, is you don't really fully understand the manufacturing process of these pixels. But what Jack did for us was help us understand some of the steps that they have to go through and that they do go through to do this assembly. And so this turns out to be extremely relevant to our discussion as we'll see.
Right, and it's Ray says here, after, by the way, we came up with our own hypothesis, didn't we, Stephen? Look, and by the way, when I say we, it's like, yeah, Steve, that's I like to think I challenged you a little, but it was pretty much Steve's education that brought me around to understanding what was happening. But right here, he confirmed this, didn't he? He used separating the chips by hand with a tool, and a person's done it, and he admitted here that they weren't necessarily careful. He understood there was an issue. But I think he said that about a few things so far, hasn't he? That he understood what.
So there's been a little bit of confusion around this issue. Probably started with the pixel survey, and then this sort of focus on the regulator. But I think that we've clarified what the true source of the problem is.
So let's get to the problem. So first, I think it's important to say you're an master's in electrical engineering. That's a big degree, a ring degree. It's not as my neighbor who is an engineer says, is not a pretengineer. You are a literal chip engineer, right?
I'm a real engineer,
right.
Professionally recognized engineer in the province of Alberta.
because I'm a Microsoft certified engineer, but that's a pretend engineer, he says. So I'm going to start with this first pixel because first there's two problems Ray had last year. One was there was issues with flickering. Another one, there was issues where it got so hot and it caught fire. Am I right?
Correct.
Right. So let's start with the first part, and let's start with the fire one, and then we're going to talk with the issues where the lights were flickering, because I think there's two different answers to this. I think you'd agree?
Yeah, well, there's often combination of an overlapping issues when we talk about sort of reliability of these pixels. There are a lot of people that experience functional failures of the pixels, and what I mean functional, I mean that the pixel stops working.
Right.
It doesn't self-destruct. It doesn't melt down. It doesn't cause a fire, but it just stops working. And then we have the probably the more concerning issue around the pixel failures that lead to a fire, and so the fires are a big concern for everybody because obviously for obvious reasons we don't want to cause a fire and burn our house down, or in the case of California, it's probably real risk here is they burn their whole state down. So it's there's two sets of issues that sort of combine, but the causes for these things are distinct and separate.
So first, I think we'd like to say thank you to the people who did this pixel survey before. This is not to take anything away from what they've done. I think they've helped us open my eyes anyway to what's going on.
No, absolutely, and like this particular video helped. Again, as much as Jack's video helped us understand this problem, I think this video actually allowed us to zero in on the exact source of the problem.
And we were lucky because as Canadians, what we did is we asked for samples, and people sent us samples, eh, Steve?
Right.
Yeah, and you got a number of samples. We don't have a lot. As a master's electrical engineer, can you guarantee that things could be safe?
What's that?
Can you guarantee things could be safe with that ring of yours?
Not guarantee.
No. The answer is no, right? You can't guarantee anything safe. All you can do is do the math to make it as safe and look for any issues. Am I right?
Well, yeah. My purpose here is just to share our findings.
Right.
I'm not going to declare a pixel safe or unsafe. What I'm going to do is try to explain what we observed, the conclusions we came to about particular pixels, so that people are in a better position to make an informed decision about, first of all, do they want to use pixels, and second of all, if they're going to use pixels, what are the things they should be aware of, and when they start using this.
So when an engineer builds a bridge, they don't guarantee the government that it's 100% safe. They just guarantee they're going to look at everything they can to find the problems.
Well, no, I mean, we're talking about things like bridge construction and civil infrastructure and stuff like that. I mean, there's a role for engineers in doing the public good. So, I mean, your engineers do take responsibility in, when they design a bridge.
In the design. Okay.
Sign off on that.
Right.
I haven't been engaged to do any sort of professional review of this.
Right.
I'm a hobbyist like everybody else. I'm using my education and my experience and trying to help others. I do see this as a public safety issue, so as part of my ethical responsibilities, I think it is part of my responsibility to bring people's attention to spread this. Beyond that, though, I haven't been engaged by anybody.
No.
To do this. I chose to do this on my own and just try to investigate this because.
And moreover, you didn't design, but you didn't design the pixels. You didn't design the boards. You didn't design any of this stuff. You're just reviewing it. Am I right?
Yeah, I'm trying to understand what's causing these failures.
And that's my way, guys, of saying, look, we're taking auxiliary information, trying to piece it together and come up with a logical output of what happened or what we can expect. And that's really my way of speaking to Steve so that everybody here is clear. We're just looking at a problem, trying to find a solution. see if we can identify it so we can avoid it later. Would that sum it up pretty well, Steve, or do you think? Sorry, we're just trying to identify a problem and see if we can try to avoid it.
Yeah. I think the best thing here is to share the information so that people are aware of some of the risk factors, and they can deal with some of the misinformation. There's a lot of misinformation in this hobby I've uncovered as well.
So let me stop you there, because I think that's exactly the point where you and I became buddies, because we started listening information. For instance, is there can water cause a fire?
Right.
Can water cause a pixel to burn? Not by itself.
Water by itself is fairly inert when it comes to fire.
So the second point I'm going to talk about,
water doesn't burn.
No. Look, it causes other issues, guaranteed. Can epoxy cause a fire? It could be. It could cause. Can it be the root cause of the fire?
Burn.
It can burn.
It's non-flame retardant epoxy. There's different types of epoxy. Some of it does burn. Some of it doesn't burn as well. But it is flammable. But in and of itself, it doesn't cause a fire. It needs an intense source.
Right. What causes fire?
To burn, right?
What causes fire?
Well, in this case,
heat.
We need some intense source of heat.
Right.
Or flame.
So with that,
to cause them.
Right. So with that being said, let's take a look at this, and I want you to tell me. So there's two photos here that we're going to want to review quickly. Is there anything particular here you want to look at?
Well, I think the thing that stands out in these images is if you zoom in on those pixels and you look closely, the thing where my aha moment when I saw this came is as I stared at that image, the shape of that intense heat source in there is what's significant. So when you actually look at that, it jogged my memory about when we were looking at the circuit boards. We're kind of going at this from the back forwards, but what we're seeing here is a very cubic type of and a very small image of this intense heat source.
Right.
And what we're probably seeing is actually not the actual heat source itself, but a reflection off the surface of the pixel.
Okay.
So that kind of skews the image slightly.
So when you're looking at these, what do you see?
But actually go to the image of the pixel, because
go back.
Actually shows the result.
Would you like me to go to the end result?
Yeah, go to the inside. So what are we actually looking at in that image? Sorry.
Yeah. Now, before we do this, I'd like to thank Travis for this photo. Travis Leader, he shared this photo with us. He did a great job taking this apart, didn't he?
So I think we were seeing in that image slightly skewed because of the optical distortion due to the surface of the pixel. So I think what was happening was this particular component was heating up to incredible temperature. It was reflecting off the surface the light of that was being emitted from the heat. The intense heat was being reflected off the surface of the adjacent pixel and then reflected again to our eyes off the surface of the pixel. So that's why we have this sort of distortion in the orientation. But it's clear that the outline of that image is very, very similar to the geometry of this particular component on the surface.
I'm just going to blow up the other one here just so that we get another point of view. So taking a look at this is just the other point of view of it, so it's kind of the same photo. I'll get you to remove there you go. So let's look at the damaged area. What do you know to be true?
Yeah, so there appears to be an incredible amount of heat generated, particularly on the left-hand side of the circuit board, but closer to the bottom of the board than to the top of the board. So it's kind of skewed in this sort of quadrant here.
Like here?
And the expansion of that, the heat kind of expanded from that point. You can see a lot of evidence of intense heat in this corner because you can see a bunch of solder is actually reflowed. So it got hot enough in this area to melt the solder, and then when that happened, all sorts of other secondary and beyond effects start to occur, and it becomes you have not just one component involved, but now you have multiple components involved in a thermal runaway situation,
So,
which ultimately can lead to a fire.
so I'm going to challenge you, and I know your answer, but I'm going to challenge you so people have this benefit of what I've learned from you. I'm going to go back to this previous video, or this previous image. Right here, what do you figure, what is that? Is this right there?
So that's the regulator.
Okay, now, go ahead.
So this is the regulator here.
Yeah.
This is what's left of the regulator here. This is actually what's called a capacitor. There's kind of very little remaining of that capacitor. I'm not sure if that capacitor is this capacitor and just it's getting moved because of the solder reflow.
Right.
It's hard to tell exactly what's going on, but our analysis leads us to believe that the capacitor that started the whole cascade of events was this one C2. That failed first, and then that intense heat source then led to the rapid engagement of other components. It started to melt solder. This capacitor would have failed due to the heat. Shortly after that, both these, this would have short-circuited the 12-volt rail. This would have short-circuited the output of the regulator, the 5-volt rail. Both of those would have got incredibly, would have generated and liberated an incredible amount of heat, which then led to the solder of the wires melting, the solder of the regulator melting, and eventually in this case, it looks like the epoxy may have caught fire. We can't really tell, but there was an incredible amount of heat.
What's this?
This is a resistor.
Right, so it doesn't look like it's too damaged there, does it?
No.
No.
The resistor, in this particular case, that particular resistor is used for, in the data line for shaping the waveform from pixel to pixel.
So your hypothesis is the fire's coming this side of the board.
Yeah.
Okay.
Yeah, and specifically this capacitor.
Right, so I'm going to clear this out. Let me clear my drawings, and then I'm going to move this photo away. And give me 1 second. So this is a photo of the fire when it first came out, and that kind of lends to what you're talking about?
Yeah, so the eruption from the casing of the bullet, I think, is very indicative of the where the pixel, the heat was being generated. So so in this case, we can see the profile of the pixel. You can see the edge of the circuit board in these images, and you can see the eruption occurs is pretty much centered at that capacitor, and we went back and started looking at other images of this pixel and images from the pixel survey, where we had other pixels that had failed, that were shared, and in all these cases, we're seeing the profile, the edge profile of the circuit board, and we're seeing that the eruption occurred in the vicinity of those capacitors. So I think we're have a high degree of confidence that the failure mechanism for these pixels in the pixel from Travis was indeed and in fact a failure of the capacitor.
Okay, so we figured that there's all kinds of math we could do that, but I'm just going to want you to talk for a quick second. I want to tie in the first video we did with this. Hold on, I got to get to the page.
So one of the things I started to think about is, okay, so why would the capacitor fail? And initially I started thinking about heat issues and whatnot. But then it occurred to me with Jack's video on the assembly of these things, and the depanelization, and that's actually one of the failure modes that are well sort of documented and researched in electronic assembly. And here's an example of one particular piece of literature out there that documents some of the causes of capacitor failures. And MLCC capacitors, monolithic capacitors, what the specific type of capacitor, and they have a particular bunch of failure modes that lead to cracking of the device, and then the cracking causes current to flow through the device, and then the current leads to thermal runaway because it generates heat, which then decreases the resistance, which increases the amount of current, which generates and liberates more heat, and you get what's called a thermal runaway. And so there's actually quite a bit of literature. There's this particular paper. I have another paper from the University of Maryland that document the failure modes, and depanelization is clearly one of the failure modes. And so what contributes to this depanelization problem is when you have one of these MLCC capacitors very close to the edge of the circuit board, and then you stress the circuit board, you can cause these cracks in the actual capacitor. And so these capacitors, being as close as they are to the edge of the circuit board, experience quite a bit of stress during this depanelization. And generally, separating them by hand is kind of the worst thing to do. You want to do some sort of mechanical, but if the mechanical separation isn't done properly, and some of the forces stress these components, then it causes failures or cracking of these capacitors. And so our belief is that this particular capacitor failed because of the depanelization. Again, reviewing Jack's video, we feel pretty confident that this depanelization process probably isn't controlled all that well. And so we see not a rampant number of failures, but we see a significant number of failures that concern us, that this problem will probably not likely go away anytime soon.
So going to that, let me pick on how many capacitors. So how is a capacitor made, and how many do you get per batch?
Well, capacitors are made it's a batch process.
And dumb it down.
They stack layers of ceramic material on interdigitated with electrodes, and these things would be made in plates, probably 12 inches or 20 inches or more in size, and then these things all get cut up afterwards. So there's literally thousands and tens of thousands or hundreds of thousands of capacitors made per plate, yeah, I guess that answers your question.
Yeah, that does. And how many? And the regulators made the same way.
So regulators it's kind of a two-step process. They're a semiconductor device. The semiconductor wafers would probably manufacture 50,000 to 100,000 of these things per wafer. They're very small chip, probably less than a square millimeter of silicon real estate inside that regulator. And then the silicon chip itself is placed inside this package you see here in this image. And then that process involves encapsulating the silicon chip in this polyamide or nylon material that has the mechanical electrical leads that actually connect to the circuit board.
So how many
And
would you
those are
get?
sold in reels, typically to the manufacturing facility. You buy those in reels, and those reels might have, 3,000 or 7,000 components on a reel of components. The chips are made in tens of thousands, and they're sold in reels of probably several
So
thousand.
so if it was a capacitor problem or a regulator problem that was the problem, you'd expect to see this in a lot more devices. Am I right?
Well, if the source of the problem was the manufacturer, and it was a batch, it was a raw materials problem. So it was a problem with like on a batch process. You'd expect to see, um, you know, big big areas of failures.
Right.
So batch failures. We'd be experiencing hundreds or thousands of these failures in a short period of time, and then nothing, right? So that this failure's really kind of not consistent with that.
No. So it does lend to what you're saying. It comes down to what do you call this? A pressure? You didn't call it. You called it to me something. A pressure crack. You described it on
It's a microfracture due to stress.
right stress crack. Sorry, yes, I apologize. And then you're talking about how it'll start vibrating. Can you explain that? Do you know what I'm talking about?
No.
See, these are conversations, but eventually it gets so hot and it'll run away.
Yeah. So when you get that sort of micro crack that happens, it creates a short circuit.
Right.
And initially, the short circuit's a pretty high impedance or a high resistance short circuit, so there's not a lot of current. But the fact that there's current through a capacitor, which there normally isn't, DC current, starts to generate heat, and then the heat causes additional failure of the capacitor, which lowers the resistance, and then the resistance being lower increases the current. And power dissipation is a function of the square of the current. So as the resistance decreases, the current's going up in an exponential manner, so the power increases. And eventually it gets so great that it starts to glow red. You get to the reflow temperature of the solder, which is typically around 250 to 300 degrees C. And then once at that temperature, the epoxies in and around the capacitors become fluid. The solder's reflowing. The things actually physically start to move around and cause other things to short circuit, which then start to liberate their own heat, and the heat actually causes the other capacitor in this particular circuit to fail as well, which then generates even more heat, and you get this cascading thermal runaway, and the heat liberation continues to grow and grow and grow.
Okay.
And then that intense heat eventually erupts out the side of the pixel, and then you expose yourself to a bunch of oxygen, and if there's enough heat, and that's I'm not a combustion expert, but I suspect the introduction of the oxygen now by the eruption of the side of the case with this intense heat leads to an abrupt flame generation, combustion, and then you get a flame.
So we looked at the fire. I'm going to keep. I know the video is going to be long. It's just going to be that way, Steve. I'm not sure we can make this any shorter. If somebody wants to watch it all, they're going to watch it all. But this speaks to the fire of the bullet pixels. Are you fairly confident this is the bullet pixel problem?
Yeah, we haven't had an opportunity to look at a lot of other regulated pixels.
We really didn't see a lot, did we?
These are actually the only regulated pixels we've evaluated at this stage. So these particular bullets, we haven't been able to go and look at others and evaluate others simply because we don't have them.
And we are expecting more. Yeah,
we are expecting more.
But
we have actually seen the square,
yeah.
A square, a regulated square, and there are probably some things that could be done around that. We've actually got another example of another design defect with a different square.
Actually, let's pick on this one if you don't mind. The 2080. Sorry, are we okay to move on to this one here? Are you okay with that for now?
Well, let's just wrap up the discussion about the bullet.
Okay.
And then we can go on to
Perfect.
the square.
Perfect. So
anyway, so our contention is that the failure here was this capacitor. It initiated the liberation of heat, which led to the rapid destruction of the pixel. And the cause of the failure of the capacitor was stress induced by the depanelization process during the assembly and the manufacture. So getting back to Jack, please everyone send that gentleman a Starbucks card. We really owe it to him because he helped me in particular understand what's going on during the assembly of these things. That's actually what's causing the problem.
It's
And it's probably not the first time that this problem's been reported. When I got into, I'm fairly new to this hobby, but as I recall some of the the earlier discussions about pixel fires when I first started looking into this in the last fall, I heard some information about some capacitor-related problem, and the way it was explained to me at the time was something to do with the way the boards, the capacitor got cut. Probably something got mixed up in the translation along the way. I suspect that the problem that led to these failures that were reported before were also stress-induced fractures of capacitors. And so I don't think this problem is actually new, but I think we have more concrete evidence now that the failure of the capacitor is actually what's causing this. And the root solution to this problem will be to modify the layout of these to move those capacitors further from the edge of the circuit board so there's less chance that stress can crack the capacitors. There are capacitors used on 5-volt pixels. They're used on resistor pixels, but there's usually only one capacitor in those cases, and the capacitors more often than not centrally located on the circuit board. So you'll see the capacitor isn't close to the edge, and so it's not likely when it's in the middle of the circuit board to suffer these stress fractures during the depanelization process. But any situation where the capacitors are close to the edge like this, there's a chance that this depanelization can actually lead to the failure of the capacitor.
And there's not much I can do at the moment to address that side of it. I'm sure with time we can communicate and deal with people that seem to be fairly open to some of your ideas so far, Steve. I'm going to carry on with the fire issue. I want to move on to the square pixel, the 2818s. We did see an issue there. You've seen an issue there, particularly.
Yeah, so this is when at the beginning of my analysis, I was doing a lot of analysis of the circuit board layouts and evaluating and modeling the traces on those circuit boards and their heat, their ability to generate heat under operating conditions. And one particular pixel kind of stands out from the others in this 2818 pixel that we looked at. We had one individual send us these pixels, and they were having a lot of functional problems with these pixels. So I'm not aware of that. This individual had any fires to report with this particular pixel, but when you model, when you look at these, where did it go?
Sorry.
When you do the analysis of these circuit boards, you look at the widths of these traces, and in this case, the minimum trace width of this particular wire here is about 0.4 millimeters. Over here, it's about 0.64 millimeters, but there's also a conductor on the other side of the circuit board that's about the same size. So the total width of copper for the plus 12 volt trace from input to output is about 1.2, 1.3 millimeters for the 12 volt trace here. But for the ground trace, it's actually, it only exists on the bottom side of the circuit board here. There is no copper on the top side of this particular board. And it necks down to about 0.4 millimeters. So when you do the analysis, and there's a couple different algorithms used for estimating the rise in temperature due to the current in that trace. There's UltraCAD published some data, and then another, the IPC, which is an international standard for circuit boards, have another algorithm for evaluating the current, the capacity of circuit board tracing. And so using the two different methods to calculate what the temperature rise in that particular circuit trace would be, it's somewhere between about 206 degrees and about 484 degrees C. That's the rise in temperature. So if ambient is, say, 30 degrees, the actual temperature of that trace is somewhere between 236 degrees and 514 degrees. And circuit board material starts to delaminate at about 130, 140 degrees typically. You get degradation of the circuit board material. Circuit board material is just typically epoxy with the fiberglass to hold it all together. And as soon as the epoxy starts to soften and melt, the mechanical integrity of the circuit board starts to suffer. And of course, when you get into temperatures that are approaching 300 degrees and more, you actually start to reflow solder. And this is a potential source of intense heat, and all that would cause, the only thing that would have to happen for this particular pixel, for this to happen, would be for a user to accidentally short circuit their pixel string and cause 5 amps of current to flow through that pixel. And so if you short circuited and there was enough, if there was 5 amps of current flowing through this pixel, you'd see these types of temperatures at that hotspot. So if anybody has these pixels, you might want to take a closer look at these pixels and inspect them. And certainly you want to be, at the very least, very cautious about your installation of these pixels and careful not to short circuit them.
So, and that's the 2811s. That's the one with the 4 wires on it, right?
It's the 2818.
2018, sorry, my bad. Sorry, yeah. The one with the 4 wires.
Yes.
And that would be each one of these down here.
Yeah.
Okay.
This is the only pixel that we've looked at so far that jumped out as an immediate
Concern.
Safety risk.
Right.
There are issues with other pixels we've discovered, and
right.
But this one, I think, requires special attention because anybody who's got this pixel and inadvertently causes a short circuit within the fusing capability of most controllers, it could lead to a severe failure and intense hotspot.
Right. So the last thing I'm going to talk about, we're going to move off from the 2818s. We're going to move off from the fire. We're going to move on some issues we've had from the same people sending in Pixel. There's people saying there was fires, and then there was performance issues. The lights were flickering every time it rained.
Yeah.
So I'm going to bring up this one here. Well, let me make this bigger. What can you tell me about this?
Yeah, so, and during this process of tearing down a variety of pixels from several of the suppliers, I started to observe certain things when I started to do these teardowns. And when I started this process, I didn't know if these were meaningful issues or not. But as I progressed, I think I've come to the point where I understand why people are experiencing functional pixel failures. So when people say the pixels get wet and they stop working, I think I understand why that's happening now. And again, potentially what the suppliers can do to address these issues. In this particular case, this was an individual who sent us some pixels that were acquired at different times in 2020. So there were some pixels acquired in April of 2020 and some more pixels acquired in October of 2020. And I believe this pixel was acquired in April. I have to go back to my notes. But when I took the teardown, I did it I kind of took a stepped approach. I would take the pixel and I would photograph the pixel. I'd cut it off to the wires. I'd do some resistance measurements before I actually cut them off. And then I would cut a pixel out of the string, and then I would photograph the pixel, usually from the top and the bottom, sometimes from the side, like you see here. And then I would go through a process of actually tearing down the pixel. And tearing down the pixel involved heating the pixel a bit. So I would essentially just boil some water, pour it into a cup, into a mug, and place the pixel in the boiling water for about 10 or 15 seconds. Remove it, cut down the side of the outer casing, and then it just peels right off. It's almost effortless to remove the outer casing from these pixels. Square pixels, you can pretty much almost remove the outer casing. You don't even need the heat to remove the outer casing. I believe it's a different material. I'm guessing that I think the material used on the square pixels is a silicone-based outer material. I suspect, and although I don't know for sure, but I suspect the material used on the bullets is probably more of a PVC type plastic. It's a little bit stiffer than the silicone that's used on the squares. Maybe the squares, and then they might just
Sure.
vary to PVC. I don't know. Anyway, so this is what the pixel looks like when you remove the outer casing. And you can see here the pins or the leads from the LED are poking out the side of the epoxy. And I noticed this on quite a few of the pixels I tore down, that in some instances these leads, that they come in this way and they bend. They go through the circuit board and they're soldered onto the circuit board. And one of the things I never really could ever explain is, why these circuit boards were always skewed. Some cases you'd have a circuit board that was nicely aligned with the axis of the LED. What you'd have, if your LED is nice and straight, you'd want the axis of your circuit board to be kind of in the same axis. But in this case, you can see this circuit board's actually quite skewed. And as a result, what ends up happening is if the leads aren't trimmed right to the surface of the circuit board, they end up pushing against the inside of the casing as they slide this thing into the casing. So imagine, in this case, I've straightened it out where the LED is generally in the same axis as the circuit board. They're pretty much parallel here. But in a lot of cases, that's not the case. In a lot of cases, this angle here is something less than 90 degrees.
Sure, but what's causing the issue?
What that does is when this goes into the casing, these pins then push against the side of the case. And then when the epoxy is injected into the casing, the tips of these pins, in some cases, actually don't get covered in epoxy. They don't get sealed. They're sealed kind of to the outside case, but if the integrity of the casing, the bond between the case and the epoxy becomes compromised.
Right, and when
there's water ingress between the case and the epoxy, it could migrate to these exposed electrical connections and cause functional failures.
Right.
If those were exposed to water and the water was, something less than pure water, it had some contaminants in it, some ionic.
So these pixels particularly
it could cause a slight, minor short circuit, which would functionally affect the circuit.
Right, and these pixels particularly were flickering during wet weather.
Yeah, so the reports are, these things start to flicker, and this makes sense. If these are being exposed to water that's got some sort of ion content, you're going to have some resistance. Might be a few kiloohms of resistance there, and then that starts to interfere with the operation of the pixel.
And especially
so I noticed this. I noticed this on bullets. I also noticed voids in and around the base of the LED on the square pixels. That there can be sometimes a void there that exposes the wires of the leads of the LED. And I also noticed, particularly on the squares, but this also is evident on the bullets, the manipulation of the wire, particularly in the cases where you don't have really rigid epoxy, that repeated manipulation of those wires creates a gap between the wire and the epoxy, and that gap goes straight to the circuit board. And if water drips on the wires and wicks up the wire, it can wick all the way to the connections on the circuit board.
So,
and again, start interfering with the data communication.
And I just like
the light.
I'm going to like to tie this back. This epoxy here was the softer epoxy, a little bit of heat.
This particular one had some. Was the person who supplied and characterized it as gummy epoxy,
right?
And it was definitely softer than some of the epoxies that I encountered.
So
some epoxies that I encountered, like I say, every one of them pretty much pulls apart with your fingernails when it gets to 100 degrees C. Some of the epoxies kind of re-solidify when they cool again. In some instances, I didn't really notice that they solidified much after they were heated, which leads me to concern that some of these epoxies, when they're exposed to higher heats, can soften and stay soft, which then may result in these functional failures. Not likely, in my view, at this point, based on what we've seen, I'm not sure that epoxy failures would result in pixel fires.
No.
But it would definitely
performance,
functionality of the pixel.
So, and let's we're going to wrap this up. We've been at this a lot longer than we had planned, but it's the only way we can get all the information in about these particular issues and pixels. Notice we didn't talk about the name. We don't have any interest in talking about the name, but people know. No. Um, I want to talk about Texas,
Yeah,
California.
this problem's pretty widespread.
Yes,
Like the problem with the
that's right. It could happen to
we
anybody.
haven't seen very many of the regulated pixels, but what I do know is that between vendors, when I looked at their 5 volts and the resistor pixels and the 12-volt resistor pixels and stuff, we saw a lot of vendors, they use the same supplier
That's right.
circuit boards.
That's right.
They share, some of these guys share the same suppliers.
Yeah.
And so I, I don't think these vendors are manufacturing their own circuit boards and manufacturing their own circuits. I think that they're buying them from somebody else who manufactures them. So, so it's likely that just because like one vendor's we identified this issue around the fire, it's very likely there are other suppliers that are using that circuit board in their pixels, and we may have a problem with other vendors as well.
Right. We don't know.
We don't know because we haven't
Right.
those pixels.
We're hyper vigilant about one, but frankly, the crunch machine, for lack of a better word, is probably where that can be a commonality between everybody. So I want to talk about the temperature. You were able to peel the stuff off quickly, 100 degrees, right? Celsius.
Yeah.
Right.
Yeah.
Easy. How hot can a roof get? I suppose you don't know right off, do you? But it can get pretty warm.
Yeah. No. I mean, you know, on a hot day on an asphalt roof,
It can get warm.
getting to 40, 50 degrees is probably not unreasonable.
Right. And imagine Texas, California.
Southern United States, it's
Yeah.
probably even hotter.
Right.
And then on top of that, you know, of course, you got the temperature rise of the pixel
Yep.
when the pixel's operating. So there's going to be, you know, a regulated pixel or a resistor pixel, either way, is going to be dissipating close to half a watt of heat just because it's on. Um, and, and so if there's going to be a temperature rise because of the operation of the pixel, there's going to be a temperature rise because of maybe these PCB traces associated with certain parts of the pixel printed circuit board, and there's going to be ambient temperature because of, you know, the outdoors and being outside.
So my last thing I'd like to point out, and it's something where you and I both kind of came in. Somebody said that 1 every 100, 1 every 1,000 pixels dying is meh, it's par for the course. Can I ask you how many parts you think is in a phone or in a car?
Oh yeah, I mean this is a big issue for car makers and
Right.
anybody that manufactures anything.
In your professional
The
job,
number of components in one of those things, you know, you can have tens of thousands of parts in the average automobile, you know.
right?
They're complicated assemblies. And so if you have a failure rate of, you know, parts per thousand, you know, no modern car in the planet would make it off the assembly line. They'd all have failures because you take those numbers times the number of parts, and you'd be guaranteed, there would be a certainty that these things would be rolling off the assembly line with at least one failure. So automotive specifications for reliability, you know, insist on Six Sigma. Generally, you got to measure failures in parts per million. And most modern electronic manufacturers are shooting for those kinds of things as well. I mean, Apple manufactures iPhones, you know, in quantities of, you know, they're tens of millions, 100 million of these things a year, times the number of components in a phone. There's probably 300 or 400 individual components in one of these things. So we're talking about billions.
Right.
You know, and they can't afford to have the failure rates, you know, in the parts per thousand. So you know, it's people might think that a part per thousand, one pixel failure in 1,000 is okay, but it's actually not
Right.
anywhere near an acceptable failure rate. These things shouldn't normally fail. You know, the failure rate should be parts per million.
Right. And frankly, it's okay if I destroy it. I get that I could be an idiot. Idiots happen. I'm installing it. I'm not a professional, nor am I automotive. But for the most part, these are just failing. The situations we're looking, they're just failing, right?
Yeah, we got two separate failures, right?
Right
One
there.
is the serious fires
Yeah.
that resulted in the heat, which are serious safety issues. And then you just got the functional issues, right? Due to manufacturing defects, which I think are controllable. Like
That's right.
aligning those LEDs would do a lot, I think, to minimize the chance that these leads can get exposed.
Trimming the
It wouldn't
leads.
completely eliminate the problem, but it would go a long way based on what I've seen. Just making sure that those, the LED is square to the circuit board, right?
Right.
And making sure that it's centered in the casing when you inject the epoxy. And that would go a long way, I think, to improving the functional reliability of this thing. And then, there's the other added issue of the quality of the epoxy. It does look like there are some quality issues around their epoxy um, uh, handling and or use of the epoxy or the material itself.
Which is a
Doing it has resulted in a wide range of different consistencies of epoxy hardness.
So, look, we're going to sum it up, Stephen. I appreciate your time right now. Obviously, we're speaking here maybe for 45 an hour. I don't even know how long it was. I apologize to anybody who stayed this long. But it was a big subject. It had to be knocked out. We wanted to knock it out. The sheer number of hours Stephen put in to go over this, the sheer number of hours he let me talk to him and try to make it so I could understand it, we owe you a debt of gratitude, Stephen. I'm sure we can't pay. And I thank you for your time and your professionalism. And, of course, moreover, as I think your logical explanation of what happened makes sense. And thanks.
Yeah, I think we've done quite a, and thanks again for you, Pat, helping me get the materials. I've been asking around for a while now, trying to find source of pixels so that I could actually tear these things down and have a closer look. And your help with that is really what enabled this to happen. If you hadn't had me do that, we still wouldn't know what the problem was.
Well, see, teamwork makes the dream work. And for the last part of it, I just want to let everybody in Canada know, if the US ends up watching this video and wants to chuck stuff at us, by all means. If you want to send us, anytime you have some dead pixels, give us 1 or 2 plus or minus. I'm going to set up an address so you can ship it to me. Stephen, you may not know this, but for the rest of the year, I'm going to keep a depository of all these ones, and then we're going to send it all at once so we can kind of see overall. Because really, we had a small sampling, didn't we, Stephen?
Yeah, we haven't had a
No, we didn't have one.
Test, but
which is why it's not fair to pick on one supplier.
Yeah, but some people, and we're grateful, particularly to Travis.
Yeah, Travis.
It was the analysis of Travis's pixel that really allowed us to zero in on this problem.
Right.
And we're grateful.
It was almost like the Matrix, eh? When we saw it, it was like, it's not the regulator. It can't be the part. And I remember we were talking about it because it would fail in a lot bigger. And then all of a sudden we got Travis, and then all of a sudden we remember Jack's video, and then you put it all together.
Yeah.
The story wrote itself.
Disconnected pieces that
right.
all came together. Again, Jack's video, we owe that guy a real debt of gratitude.
Actually, there was all kinds of people in Canada at their own expense shipped us pixels. We appreciate it. And we are, as pixels go on, we are going to request that I'm going to keep a depository of all the pixels, where they came from. That way we're going to be able to keep track of what the failures are. Look, it's human failures. That's fine. We can accept that. We just kind of want to know what it is. Stephen, I think we're going to knock this out. I appreciate your time. You rock. If anybody has any questions, of course, Stephen and I are going to be available at any particular time. We're fairly open and responsive, eh, Stephen?
Yeah.
Appreciate it. Thanks, guys.
Yeah.